Here we're going to evaluate the expression of our logs. And this first part we want to do without a calculator. We will run into some that we will use one in a bit. So just a little uh, reminder, don't overthink logarithms. All they are exponents. And so you can see the conversion right here. So if you have log base b of x equals y, you convert that into b to the power of y is equal to this value right here, right? So basically, if you look at this first one, what you're trying to do is figure out 4 to what power gives you 16. That's what's being asked right here. See, b to what power will equal the value right here of the logarithm, okay? So right here, basically, if you want to, you could even write it down. 4 to what power equals 16? And this one's not too bad. It's 2. 4 to the second power is 2. So 2 is the actual answer. So that's our answer for that one. And so if you want to, feel free to write it in that format. Basically, you're going to convert it to exponential form because that's all logs are. Like I said, don't overthink it. So on this next one, we're going to have 2 to what power equals 64. And so you might be a little unsure about that one. You might have a good guess, but what you might want to do is basically start like a little 2 times 2. Okay, that's 4 times 2. That would give me 8 times 2, 16 times 2, 32 times 2, 64. So it took me 1, 2, 3, 4, 5, 6. It took me 6 factors of 2 to reach 64. So that is my answer, 6 right there. So 2 to the power of 6 is 64. Okay, as we move forward, some of these will be a little tricky. I mean, they're not going to be that bad. They're kind of fun, I think. But it's just using, honestly, it's using stuff you should already know from uh, previous topics that we have covered. So here we go. So 5 to what power will give me 1/5? And so, what would cause this to become a reciprocal of itself, right? And so that would be -1. If you raise it to a negative exponent, it causes you to take the reciprocal, and that's where the 1/5 comes in. 27 isn't too different than the previous one. So 2 to what power would give you 1/8? So you're trying to figure out what would cause it to turn into 1/2, and then how's that 1/2 turn into 1/8? And the answer is -3. And if you want to, you can check it. So 2 to the -3 power. That negative causes it to become the reciprocal. So now it's 1/2 to the third power. 2 to the third power is 1/8. And so it just kind of takes practice. Like I said, we've covered properties of exponents previous to this lesson, so you're going to have to recall all that stuff. And if you have all those rules down, it's really not that bad. Like I said, logs are just exponents. Don't think too far into it. Okay, so on our next one, looking here, we're doing 7 to what power would give me the square root of 7? Okay, once again, this is something we discussed in class, but you might have forgotten, okay? And so exponents, particularly rational, fractional exponents, are the same thing as radicals, as our radicals. So here's a little side note. So if you have some base raised to a power of, let's just, I don't know, I'll call it x over y, that is equivalent to the y root of b raised to the power of x. Okay? Um, so as you can see, you're taking the square root, so that would mean the y value in this case would be a 2, and then you have an understood power of 1 right here. So that means that if I were to convert that into exponent form right here from radical to exponential form, that would be 7 to the power of 1/2 right there. And so hence, what I'm trying to solve for right here, that question mark is going to be the 1/2 right there. So the answer is 1/2. Okay, 31, pretty similar. So we have 2 to what power is going to give us 1 over the square root of 2. So this is a combination of problem 29 and problem 25 up here. It's a combination of the two because you have a reciprocal taking place, but then you have a square root. Okay, so the reciprocal is going to mean that my exponent's negative, and then to turn it into a square root, that means that my exponent's got to be 1/2. So combine that together, it's negative 1/2. That is my answer. And just to kind of show you over here on the side, so 2 to the negative 1/2 power. So the negative would cause me to become a reciprocal, so 1/2 to the 1/2 power. And then when I convert this from exponential form to radical form, the denominator is 2, so that means square root. And then my numerator is 1, so that just stays a 1 up there. So it's just square root of 2. And the 2 and the 1 are understood in the radical. And so just kind of showing you that that answer does work. Okay, let's try another one here. This one throws folks off a little bit, so let's see. We're going to have 64 to what power gives me 8? So everybody kind of gets a little thrown off here. They think it's 2, right? Because 8 squared is 64. But what we're trying to figure out instead is 64 to what power would give me 8? So they're like, well, I could divide by 8. Well, but we're dealing with the exponent right here. And so the answer is actually going to be 1/2. And the reason why is if you have 64 to the 1/2 power, that's the same thing as the square root of 64. Square root of 64 is 8. So that's where that 1/2 is coming from. Okay, here we're going to look at some of our properties, and these can help us whenever we're trying to manipulate these in a later section. Um, and some of these are going to seem pretty obvious and others might not. But so right here, if you have your base of what you're evaluating is the same, it automatically equals 1. So for example, right here, if you look at this, you're asking yourself 5 to what power gives me 5? Well, that's kind of silly. 5 to the power of 1 would give me the same thing in return. So 5 to what power gives me 5? Or in terms of the property, a to what power gives me a, and it'd be 1. Okay, so if these match, automatically it simplifies to a 1. On this next one, log base a of 1 equals 0. And that property right there, that's because anything raised to the power of 0 equals 1, right? Except 0, but that's not going to happen. So as long as you have something other than 0 as your base, which you always will, uh, and we'll talk more about your restrictions on your base later, it's going to equal 1. So for example, right here, 4 to what power would give me 1, and that's going to be 0. So once again, that's one of our exponent properties that we've discussed in the past. Okay, what if what I'm evaluating already has a power right there? Well, basically, that's going to be your answer is the power right there. And so, for example, right here, 5 to what power gives me 5 to the power of 7? Well, in order to make the two sides equal, my unknown would have to be 7. So that's pretty easy to understand. The last one throws people off a little bit, but if you kind of think about it, it does make sense. But right here we have a raised to the power of log base a of x, and that's going to equal what's being evaluated right there. So the answer to number 41 is going to be 19, okay? Now, I'm going to go ahead and show you why that is. When I show you the conversion, you'll see why. So let's say I don't know what it is. Let's just say it equals, whatever, x, okay? Now, what I'm going to do here is I'm going to use this right here. I'm going to convert from exponential form right here. What I'll do is I'll convert from exponential form back to log form, and then it will be very obvious of why this holds, okay? So I'm going to take this and convert it back to log form. Okay, so that's what I'm going to do here. So what's going to happen is this is going to become, so this becomes my base for my new log. So log base 8, and then my x is my unknown right here, okay? And then it equals what the exponent was up here, which is log base 8 of 19. And so you can see that the two sides are equivalent, except that the unknown right here is 19 on the other side. So hence, the unknown must be 19. And there we go. Okay, so that's the only one that could throw students off a little bit. But like I said, if you convert it from exponential back to a log format, um, then it seems pretty obvious of why the answer is the value that's being evaluated up there. Okay, so in previous videos, this has already been discussed, but we'll just talk about it again for a minute. Uh, log functions with base 10 are known as our common log. Okay, so uh, the function log base 10 of x, we usually just express it as log x. Okay, you can go ahead and include the base if you want, but since it's our common log, kind of like with square roots, we don't write the 2 when we do our square root symbol. With log base 10, we typically don't write the base there, but like I said, if you do, that's fine. So calculators are going to have a log key, LOG. I'm going to be using my virtual graphing calculator, but a scientific calculator is perfect. Even your phone's probably fine. Your phone calculator will probably be just fine. Okay. Um, Also, we have another type of logarithmic function with base e. Remember e? Okay. That's going to be known as our natural logarithm function. And so once again, instead of writing log base e of x, we do have a shorthand for that, and that's going to be ln. Okay, and that stands for our natural log right there. And yes, there is an ln key on your calculator once again. And I'll pull up my calculator just to show you all these buttons real quick. So I have right here next to the 7, to the left of the 7 is my log button, and to the left of the 4 is my natural log button. Okay, and like I said, if you have a scientific calculator, it's going to have those buttons also. And then your phone, if you turn it sideways, typically uh, you'll see that button in there when it shows you your extra keys. Um, okay, so I'm going to go ahead and simplify these once again without using a calculator. And so what we're doing here on 81, this one's, you might be log of 100. The hardest thing in math a lot of times is trying to figure out what they're asking. So what you have to remember is the base here, it's understood as 10 because they didn't write it. So they're basically asking you 10 to what power gives you 100. So 10 raised to the power of 2 is 100. That's your answer right there. Done. That's it. Okay. Here on the next one, they're saying 10 to what power would give me 10 to the power of 7? Well, that would be 7. So once again, I'm actually using, that one uses the property up from up above. So remember these properties up here. Okay. This next one's using the property we had just gone over up above right here. So you have 10 raised to log base understood of 10 equals 33. So that's the answer. The answer is 33. Don't overthink it. If you need to, you can rewind the video and see why that is. And you could even practice the conversion if you want. But that's what it's going to be right up there, 33. Okay, 87. Okay, so natural logs. So I know y'all aren't used to seeing that yet, but we're going to use that quite a bit. So that's just like, it's understood as a base e. So what are they asking? And we're trying to figure out what this equals. So if you remember, if you convert this to exponential form, it's going to be e to what power equals 1. And you have to remember that any number raised to the power of 0 equals 1 as long as that number is not 0. But that's that. We're never going to throw one of those at you like that, okay? So E, which is that number 2.7, so on, right? Um, so raised to 0 is going to equal 1. So that must mean that our unknown that we're looking for is 0. That's the answer to number 87 is 0. Okay, on 89, 89 is actually a lot like 83, okay, because it's 10 to what power gives you 10 to the power of 7. Well, see right here, your base is e, so e to what power would give you e to the power of 6. 6. That's it. That's the answer. Okay, 91 has a little bit more going on here. And so what you can do is, there's a couple of different things you can do. You could manipulate this and write it as natural log of e raised to the negative 6. So I took the reciprocal and the exponent became negative. Now I have the property where these two match each other, and so my answer is automatically right here. It's negative 6, and that's my answer. That's it. Okay, so basically I was able to rewrite it like 89. I had to manipulate this to the reciprocal, which then changes the sign of my exponent, and then that's my answer right there. Okay, 93. So we have e raised to the natural log of 125. So once again, those match. So the answer just defaults to that 125. And once again, if you want to play around with the conversion, actually, I'll go ahead and do it so you can see it again. So let's say, okay, what does this equal? We don't know. Let's convert this to log form. So what we're going to do is we're going to have log base e of I don't know equals the natural log of 125. Okay, so what you want to know is these two things are the exact same. Those two things are the exact same. Log base e is the same thing as natural log. So in this parentheses, we don't know what it is, but if we want this to be equal, it must be the same as what we have over here. So it must be 125. Okay, and then our last one, 95. So once again, since our base matches what's being evaluated and we have an exponent, the answer is the exponent. It is the exponent, which is going to be 9x. And kind of like the previous problem, if you wanted to convert this from log form to exponential form, you would say, okay, e to what power equals e to the power of 9x? Well, the unknown must be the 9x, so I'm just converting it. So one of the biggest things as you tackle this unit is making sure you understand this right here. That's going to help you out whenever you're having any problems. Typically, if you convert from one form to the other, typically that's going to help you solve your problem. Okay. Okay. The last thing that I wanted to look at is oops, too far, is evaluating these with the calculator, because now we can't quite do this in our head. We could probably guess and maybe get close. But so looking at number 55, you'll notice that this is the common log right here. So it's base 10, right? And what does this equal? I don't know. I kind of have an idea, but let's write this in exponential form so I could kind of grasp it a little bit better. So we're asking 10 to what power would equal 3? So something, well, 10 to the power of 1 equals 10. So how's this going to turn into a 3? Okay. Well, fortunately, we have our calculator, so we're going to go ahead and just plug this in here so we can see what this looks like. Turn this on. All right, so let's see. So I'm going to type log. So see, my base is understood as 10. I just put in my 3. Press enter. So it's 0.4771. And so we're going to go ahead, it says round 4 decimal places. So 0.4771. Okay, and so I'll go ahead and prove to you real quick that that is approximately correct. So if I take 10 and I raise it, I'm going to raise it to the power of 0.4771. Press enter. Look at that, 2.99985. So very close to 3. Okay, so right now we're just getting estimates. We're not getting exact answers. These are estimated. Okay, so let's try 57. So once again, just kind of give us a clue of what we're looking for. We're asking for 10 to what power gives us 532. Okay, so a popular SAT question is, what two integers is my answer between? And so I like to bring this up and just kind of have students kind of think about this for a second. So is my answer between 1 and 2, 2 and 3, 3 and 4, 4 and 5? So think about it for a second. Is my answer, it's going to be a decimal, obviously, but it's going to be somewhere between 1 and 2, 2 and 3, or 3 and 4, or 4 and 5. Okay, and so the way you could figure that out if you were taking the SATs is 10 to the power of 1, well, that's 10. 10 to the power of 2, okay, well, that's 100. 10 to the power of 3, oops, 0. 10 to the power of 3, that's going to be 1,000. Okay, so I'm looking for what gives me 532. So my answer has to be somewhere between 2 and 3. So now we'll go ahead and put that in our calculator. So let's see, log of 532. And there you go. Sure enough, it's between 2 and 3. So it's 2.7259. 2. Let's see, what was that? 2 or 7,259. So that's 4 decimal places right there. Okay, looking at 61, once again, I want to write it down in exponential form to kind of think about this. So 10 to what power would give me -2? That's a weird, let's see. Well, let's go ahead and just plug it in. Let's see. So log of -2. Non-real answer. Error. What is going on here? Well, if you kind of think about this for a second, how does my answer become negative? It can't actually. If your exponent is even if it's negative, so if I had 10 to the -1 power, that won't make my answer negative. That would just make it 1/10, right? So if my exponent's negative, I do reciprocal. It doesn't change the sign. So basically, that's not going to be possible. So we're just going to put no solution. Okay, so no solution. We can't do that. Okay, and we're going to talk a little bit more in depth about that, especially when you're graphing, because you cannot evaluate logs at negatives. You can't even evaluate them at 0. So for example, if you had log of 0, that's actually impossible too, because 10 to what power gives you 0? And even if you put a 0 there, 10 to the power of 0 actually equals 1. So that's not even possible either to have a 0 there. And so, like I said, we'll talk more about that later. Okay, so I got a couple more of these where we're just going to put them in the calculator. 63 and 65, really not much different than what we're doing on the previous ones. The only difference is your base is an E, which is fine. And we're going to go ahead and use the natural log key in our calculator. So natural log of 2, which will be 0.6931. So 0.6931, there we go, that's our answer. And now we'll go ahead and try this one right here. So let's see, natural log of 809.3. And let's see, 6.696. We're going to have to round that to a 6.2. So yeah, be careful when you're doing your homework to make sure that you're rounding properly. So on this one, I had to round that that fourth digit up to a 2 because the value afterwards was 5 or higher. So if it's 5 or higher, you got to round up. So if you look at the other one, I had 0.69314. See that 4? Since it was a 4, I didn't round up on that previous one. Okay, the last thing that we are going to look at here is the use of common logs and natural logs to evaluate some of these where our base is not common or natural. So if you look at number 69, my calculator defaults to base 10. I don't have a base 4 key function. I don't have that. Some of your newer calculators actually do, where you can adjust it, but probably most of us aren't going to have access to those, okay? So if I can't change my base within my calculator, I have to use this thing called the change of base formula, and it's very easy to use. So looking at this right here, if I have log base b of m, where b and m are just positive numbers, okay, it doesn't really matter what they are. What you can do is you can take the log base of a of m and divide it by the log base a of b, where a is probably, you're using your common log or your natural log. So for example, you would do log of m over log of b, or you could do natural log of m over the natural log of b, and that will get you your answer. So looking at number 69, what we're going to do here is we'll write this as log of 4 divided by log of 100. And that will actually give us our answer. Okay, so here we go. So let's see, log of 4. Now this is very important. Close your parentheses there. And then divided by log of 100. Close your parentheses right there. Okay. And if you're using a scientific calculator, you should be fine. Even if you're using your phone, you should be fine. But just be careful, play around with it. Make sure you know the way to properly put it in there. By the way, these calculators you are able to download for free for, I forget what it is. It's a couple months you can have these for free, so you might want to look into that. Okay, so we'll go ahead and press enter. And so let's see. Oops, I did that wrong. I'm so sorry. Let me fix that. I'm sorry. Y'all probably yelling at the computer screen. Sorry about that. Let me fix that real quick. That should be log of 100 over log of 4. I'm so sorry. Okay, so let's go back and fix that. So let's see, log of 100 divided by log of 4. There we go. Sorry about that. Okay, 3.3219. So 3.3219. I'm so sorry. I'm sure I was confusing many of y'all. Okay, and so then once again, just kind of prove to you that that's correct. We're going to go 4 raised to the power of 3.3219. And we'll see that it'll be really close to 100. 99.996. So once again, we're coming up with estimates, right? Okay, sorry about that. My bad. Okay, if we look at 70 here, so once again, I can do log, or if I really want to, I can do natural log. It really doesn't make a difference. So natural log of 17 over natural log of 0.5, okay? And I could have used natural logs on the previous one if I really wanted to. It doesn't matter which one you use. So let's see, natural log of 17 divided by natural log of 0.5. Now you can't mix and match though. If you start with natural logs, you got to do it top and bottom. Same thing with log. Okay, let's see what we get. So we get negative 4.0875. That'll round to a 5. So let's see. Approximately negative 4.0, let's see what we say, 875. Okay. And so you might be like, wait a second, how did I get a negative result? You can get negative answers. It's just these can't be negative, okay? What your base or what you're evaluating can't be negative, okay? But your answers actually can be negative, okay? Okay, the last thing we're going to talk about, and that kind of refers to what I was just speaking of right here, is the domain of these, okay? So it says find the domain of each logarithm function. Hint, logarithms can only be evaluated at positive values, okay? So right here, this can only be positive. So it's pretty simple. You're just going to take this and say, okay, what makes it greater than 0? Because it has to be positive, so it's got to be greater than 0. That means that's what that means by being positive, right? So we'll go ahead and solve that. So we'll subtract by 4 on both sides. So we get x is greater than negative 4. And then using our interval notation, so our domain would be from negative 4 to infinity. So you can evaluate this logarithm function. You can plug in values for x as long as they're greater than negative 4. Okay, now we'll look at the other one. So this logarithm right here, log of 2 minus x. So once again, that expression has to stay positive. So it has to stay greater than 0. So we'll go ahead and solve this. So we get negative x is greater than negative 2. And so I need to fix that. I don't want that to be negative. So we'll divide both sides by negative 1. So now you have to remember the rule that when you divide by a negative and you're dealing with a inequality, you have to reverse the direction. So it's going to go from being greater than to less than, and then -2 divided by -1 is +2. So our domain is all the x values that are less than 2. So all values less than 2, well, there's a lot of values less than 2, so we're going to say -infinity all the way to 2, but not including 2. Okay, so coming in here, whatever you plug in has to be less than 2 to where you can evaluate that log function. Okay, hope this helps.